Here's something that should bother you. We put boots on the moon in 1969, with computers less powerful than a modern toaster. And until the Artemis mission a few days ago, the farthest any human being has traveled from Earth is about 400 kilometers. That's the International Space Station. That's roughly the distance from New York to Pittsburgh. Jupiter, meanwhile, is sitting out there at 630 million kilometers, a number so large it basically stops meaning anything. So let me make it mean something. If you drove a car to Jupiter at highway speed, non-stop, it would take you over 800 years. Your great-great-great-great, you get the idea, grandchildren would arrive. And yet NASA has actually studied this, not as science fiction, as engineering. In 2003, NASA published a study called HOPE, Human Outer Planets Exploration. And the name is doing some heavy lifting there, because HOPE is exactly what you need when you read the requirements. The conclusion? A 6-person crew could reach Jupiter's moon Callisto and return. Trip time, about 4.5 years. Required spacecraft mass, somewhere between 500 tons assembled in orbit. That's roughly 2 to 6 international space stations bolted together. Launch date, no earlier than 2045. And every single technology required to pull it off was, and still is, years from being ready. But, and this is the part that matters, nothing about it violates the laws of physics. It's not impossible. It's just extraordinarily hard. Let's start with the most fundamental challenge, getting there. A round trip to Jupiter requires 18 to 24 kilometers per second of delta V. That's the total velocity change your engines need to produce. For context, a Mars round trip needs about 1/3 of that. And the rocket equation is not your friend here. With conventional chemical rockets, the kind that got us to the moon, roughly 93% of your spacecraft's total mass would have to be fuel. You'd basically be flying a gas tank with a small room taped to the side. That is, technically speaking, a non-starter. So you need nuclear engines. Nuclear thermal propulsion heats hydrogen to extreme temperatures by running it through a reactor core, doubling your fuel efficiency. NASA and DARPA were actually building one, a program called Draco, aiming for a flight test by 2027. And then, in May 2025, it was canceled. Budget zeroed out. The reasoning? SpaceX's Starship had gotten so cheap that DARPA decided the economics no longer justified the R&D. Which is a bit like canceling your marathon training because Uber exists. The real workhorse for a Jupiter mission would be nuclear electric propulsion, NEP. Instead of heating propellant directly, a nuclear reactor generates electricity, which powers ion thrusters that accelerate tiny amounts of propellant to enormous speeds. The fuel efficiency jumps by a factor of 5 to 10. The trade-off? Thrust. These engines produce about as much force as a sheet of paper resting on your palm. They're slow to accelerate, but they never stop pushing. And over months and years, that whisper of thrust adds up. The HOPE study envisioned reactors generating 6 to 8 megawatts of electricity, roughly enough to power 5,000 homes, driving thrusters that could get a crew to Jupiter in about 2 years per leg. The problem is that the most powerful nuclear reactor anyone has ever operated in space produced about 1 kilowatt. So we need a 1,000-fold increase. It's the difference between a flashlight battery and a power plant. Achievable, engineers say. But not quickly. Now let's say you solve the engine problem. Congratulations. You've earned the right to face the much harder one, radiation. Jupiter has a magnetic field 20,000 times stronger than Earth's, and it creates a radiation environment so intense that the planet is essentially surrounded by a kill zone. At Europa, the moon everyone is most excited about, an unshielded human would receive a lethal radiation dose in a matter of hours. At Io, the innermost large moon, you'd be dead in minutes. But the danger doesn't start at Jupiter. It starts the moment you leave Earth's magnetic field. Galactic cosmic rays, ancient particles blasted across the universe by exploding stars, deliver a slow, steady dose of about 1 to 2 millisieverts per day in deep space. Over a 5-year mission, that's roughly 200 to 4,000 millisieverts total. NASA's current career limit for astronauts is 600. So a Jupiter crew would exceed the legal radiation limit by a factor of 4 to 7 before they even got to the hard part. You might think, just add more shielding. And you'd be partly right. Hydrogen-rich materials, polyethylene, water, are the best passive shields because hydrogen atoms are close in mass to incoming protons and absorb their energy efficiently. 20 grams per square centimeter of polyethylene cuts the dose roughly in half. But here's the cruel twist. Pile on too much shielding, and the cosmic rays smash into the shielding itself and produce showers of secondary neutrons. Past a certain thickness, adding more material actually increases the dose inside the spacecraft. So researchers are exploring active magnetic shielding, superconducting coils generating powerful magnetic fields around the ship to deflect charged particles before they arrive. Simulations suggest a 7 Tesla system could bring doses within career limits. But no superconducting magnet has ever operated in space, and magnetic fields can't stop neutral particles. The realistic answer is probably all of the above. Fast transit to minimize exposure time, passive shielding, storm shelters for solar flares, and operational rules that keep the crew away from the worst radiation zones, which means, critically, staying away from Europa's surface. Quick detour, because I know you're thinking about it. The asteroid belt. Every movie ever made wants you to believe it's a dense field of tumbling rocks that requires Han Solo-level piloting to survive. The reality? The asteroid belt is spectacularly empty. It spans a region that could contain more than 30 million suns, and the average distance between asteroids larger than a kilometer is about 965,000 kilometers, 2.5 times the distance from Earth to the Moon. The chance of hitting one is less than 1 in a billion. At least 13 spacecraft have already crossed the belt without incident, starting with Pioneer 10 in 1972. None of them performed evasive maneuvers. When NASA wanted the Galileo probe to actually photograph an asteroid during its crossing, they had to go out of their way to find one close enough. Standing on a belt asteroid and looking up, you wouldn't see a sky full of rocks. You'd see stars. Your nearest neighbor would be a faint dot, if you could spot it at all. The asteroid belt is a problem that Hollywood invented, and reality politely declined to participate in. So now we're at Jupiter. You can't land on it. It's a gas giant with no solid surface. Atmospheric pressure increases relentlessly with depth, reaching millions of bars in the interior. But a crew in the Jovian system isn't there to step onto Jupiter. They're there to be something Earth-based robots can't: a real-time command center. The communication delay between Earth and Jupiter ranges from 33 to 54 minutes one way. That means when a rover on Europa hits a problem, ground controllers won't even know about it for an hour, and their instructions won't arrive for another hour after that. A crew orbiting nearby or stationed on Callisto could respond in seconds. They could deploy atmospheric probes into Jupiter at multiple latitudes simultaneously, something the single Galileo probe couldn't do, and adjust parameters in real time based on incoming data. The Galileo probe, by the way, survived only 57 minutes during its 1995 descent, transmitting from a depth of 180 kilometers before being crushed. It entered what turned out to be an anomalous dry spot, and the question of how much water Jupiter's deep atmosphere actually contains. The single most important measurement for understanding how gas giants form remains unanswered 30 years later. But the moons. The moons are where this story becomes something bigger than engineering. Europa has a saltwater ocean beneath its ice shell, an ocean containing roughly twice the volume of all the water on Earth. That ocean has likely persisted for 4.5 billion years. It sits on a rocky seafloor where water-rock chemistry could mirror Earth's hydrothermal vents, the very environments where life may have first emerged on our own planet. NASA is developing cryobot concepts, nuclear-heated probes designed to melt through Europa's 10 to 30 kilometer ice shell and reach that ocean. Operating those probes would require real-time human oversight that a 66-minute communication delay makes nearly impossible from Earth. Io, the innermost Galilean moon, hosts over 400 active volcanoes, the most geologically active body in the solar system. Ganymede is the largest moon anywhere, bigger than Mercury, and the only moon with its own magnetic field. And Callisto, quiet, ancient, battered Callisto, is the one place in the Jovian system where humans could actually survive. Callisto orbits far enough from Jupiter, 26 Jupiter radii, to sit outside the worst radiation belts. Surface radiation there is about 0.1 millisieverts per day, which is actually lower than what astronauts experience on the ISS. Its surface is ancient and geologically dead. No volcanoes, no tectonics, just a 4.5 billion-year-old record of the solar system's violent youth. And roughly half of that surface is water ice, meaning a crew could split it into hydrogen and oxygen for fuel and breathable air. The HOPE study designed an entire surface base for Callisto, inflatable habitats, a 250-kilowatt nuclear power plant, ice harvesting rovers, and reusable landers. The operational concept was elegant. Astronauts on Callisto's surface would teleoperate a submarine exploring Europa's ocean via relay satellite, while simultaneously excavating some of the oldest unaltered material in the solar system from beneath their boots. The dangerous, radiation-soaked work would be done by expendable robots. Human judgment, the ability to improvise, to notice the unexpected, to decide what matters, would be applied from safety. 3 robotic missions are about to give us the reconnaissance we need. ESA's JUICE spacecraft, launched in 2023, arrives at Jupiter in 2031 and will become the first probe to orbit Ganymede in 2035. NASA's Europa Clipper, launched in 2024, reaches Jupiter in 2030 for 49 close flybys of Europa, carrying instruments sensitive enough to detect individual bacterial cells in ice grains ejected from the surface. And China's TIANWEN-4 aims to become the first spacecraft to orbit Callisto, specifically mapping the very terrain where humans might one day set up camp. Together, these missions will answer the questions that determine whether a crewed expedition shifts from extraordinarily difficult to necessary. If Europa's ocean shows chemical signatures of biology, the calculus changes completely. Not because the engineering gets easier, but because the reason to go becomes overwhelming. A crewed mission to Jupiter requires at least 10 major technologies to mature simultaneously. Megawatt space reactors, high-power electric thrusters, radiation shielding, artificial gravity habitats, closed-loop life support, multi-year food systems, deep space crew autonomy, orbital assembly at unprecedented scale, long-duration cryogenic fuel storage, and planetary protection protocols to ensure we don't contaminate the very oceans we're trying to study. Not one of these violates known physics. Every single one is an engineering problem with an identifiable path forward. The gas giant is patient. It has been churning through its hydrogen atmosphere for 4.5 billion years. Its moons quietly harboring oceans that may hold the answer to the most profound question we can ask. Is life something that happens everywhere, given enough time and chemistry? Or is Earth a freak accident in an empty universe? We have the physics. We have the math. We even have the design studies sitting in NASA archives. What we need now is the will to turn engineering problems into engineering solutions, and the patience to let a generation of builders do the hardest thing our species has ever attempted. Jupiter isn't going anywhere. The question is whether we are.